Hello everyone, it's February 25th. Didn't do this last night because I was stuck and frustrated and angry with Fourier transform. I finally started to learn Fourier transform. Oh, this sucker is tough to to reason with. But after I've been fighting for I think 2 days, and not just Fourier transform, right, and also the Dirac delta equation and Laplace transform, and solving differential equations and convolution. So all of these coming down to one thing: integration. If you have really strong integration skill, these things will be a bit easier to deal with. But a lot of the times, the function involved, they are not regular functions, like the delta function, right? It's not a function. It's a distribution. And when you integrate this, the rules seem to be, seems to change. And also, there are stuff that I don't know, right? Like, I know that for a function to go through Fourier transform, it has to approach zero as the variable. The independent variable approaches positive and negative infinity. Right? This one I know. But when I was using Laplace transform trying to solve some differential equations, I didn't know that for Laplace to work, by definition, the function has to be um, defined from 0 to infinity, and as you go to infinity, it approaches 0, and the negative side has to be 0, right? We don't consider the negative side, which makes sense because most of the time, the differential equation uh, handle time, like the variable is time, and the negative time doesn't make sense in most of the engineering purposes. So this I don't know. So I was struggling last night because there was one solution for the differential equation that the ones I have lacks the heaviside function. I was like, why do you add the heaviside function? I checked through, all the tables for the Laplace inverse Laplace transform, and then the ones that include the heaviside function that doesn't fit my current function, right? This doesn't make any sense. And then I try to look online, and then I didn't quite understand the way that people do integration because I'm just out of practice. But thankfully, after lots of math exchange and lots of Wolfram, I was able to figure out what actually goes. Yeah, it's because for the function to go through Laplace, it has to be uh, zero when the t is negative. So the easier way to ensure this is to always put a heaviside function onto the function that is going to go through Laplace transform. So this is just stuff I don't know. But by the way, I was trying to solve a I was trying to see how to solve a differential equation that involves the delta function. And the YouTube that have this explanation doesn't really help very much. I mean, the ways that the videos on YouTube does, like I know how to do it, but the ones I'm stuck with, the delta function, like I don't know how to solve it. So I put it on Wolfram Alpha, right, on a Wolfram, and they allow you to do differential equation, but after I got the results, which is the correct results I was looking for, and I was trying to go for step by step, and then they tell me now you have to sign up for Pro, otherwise you cannot see the step by step. And the Pro is like $7 a month, and I was very tempted, like okay, I'm just gonna do this, but it's only gonna be like one question I want, so I search online, how can I get the Wolfram step by step for free? And you know what? There are people online, they offer links to a special, I think, the special server that has, I guess, pro subscription to Wolfram, and you can use it for free. So I went there and I used it for free, and it's not called Wolfram; it's called Wolfree. And but it didn't help because the way that the step by step solves, the problem I have is when I solve it, I don't have the heaviside function. And that's because I didn't realize you have to add a Heaviside function. And the step-by-step from Wolfram also doesn't have a Heaviside function. But in the actual solution, it includes the Heaviside. So I was like, what the heck? How could you step-by-step doesn't have the Heaviside, but your actual solution has the Heaviside function? And I didn't understand initially, but now I do. But anyway, it's good. I think Fourier transform is very important. And the only way to learn it is just to go through this struggle and trying to prove every single thing that I can prove, which I can. And there's just a lot of tricks in integration, like the proof of convolution. The Fourier transform of the convolution of two functions is the product of the Fourier transform of each function. Like that thing can be proved by some tricks in integration, like the change of the integration, change the base of the integration, and things like that. So I think overall it's good. It helps. A little bit of practice, get good on the Fourier. But again, like I think there's one more thing I want to do with Fourier is I want to go through the YouTube series of 3 Blue 1 Brown. He had a series on Fourier, and I will go through that, see how he explained it, and he has very 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 good graphics. So I'm gonna check that. That will be the last one, and I think after that I'll be more than ready for next week, which I think is fast Fourier transform, the algorithm, and some other application of Fourier transform. All right. Okay. After the babble, let's do the thing. We're gonna have to compare version numbers. All right. Last time I did it was September 9th, 2020. Okay, we're given two version numbers. Yes. Version number consists of one or more revisions joined by a dot. Each revision consists of digits and may contain leading zeros. Every revision contains at least one character. Revisions are zero indexed from left to right, with the leftmost revision being revision 0, the next revision being 1, and so on. For example, 2.5.33. Yes, I know these. To compare version numbers, compare their versions from the left to right. Revisions are compared using their integer value, ignoring any leading zeros. This means 1 and 001 are considered equal. If a version number does not specify revision at an index, then treat the revision as 0. For example, 1.0 is less than 1.1 because their version zeros are the same, but their version 1s are 0, so 0 is smaller than 1. Okay, return the following. Minus 1 is version 2, okay. So that's 0 because that's the same. That is also 0, which means it is treated as 0, okay. Wait, how many revisions? On digit and dot, a valid version numbers can be stored, okay. Wait, didn't say how many versions can we have, right? Yeah, I think it can, yeah, because that's revision, right? That's just the revision 2, you have revision 3, 4. You can keep piling up the dots, doesn't matter. Okay, 0.1, so this is smaller, so I'm going to turn -1. All right, how do we solve this? So everything will be something point something, right? One or more, yeah, it says one or more, so it could be more. Wait, can we do point? Yeah, let's try. Return, I don't know, return 0. Okay, and I just want to try. Let's say, can I do this? Kind of implicitly say I don't have the second revision, but I have a third revision. Have oh no, okay, it's not good. So that's simple, right? We just split based on this and zip zip eh should we zip? What about a different length? Well, if it's different length, right? So we zip it and then we compare the length. If oh actually no, we have to no, I'll have a zip longest, right? We can zip longest and I actually don't know. I forgot. Let's check zip longest. I think that's iter tools. Iter tool has zip longest. Can you provide default value for zip longest? Change zip longest. Okay, zip longest. Iterable fill value. Yeah, you can do fill value. I just fill value to 0 and then compare the two. Okay, so yep, that will be the solution. Oopsie doozy, just made a poo poo. Stop 2 is 2 5 for today. All right, let's go back here. I need iter tools. All right, so let's say from iter tools import. What do we import? Zip longest. Okay, and then what we can do is compare each. We int each. All right, if from left to right, if anything left is smaller than right. Okay, if left is smaller than right, then okay, so what we do is for, let's say, v1 and v2 in zip longest version 1 dot split dot, right, and version 2 dot split dot, and I think it's called fill value. Okay, fill value equals 0. Oh, we have to go this because one inted. Okay, so we will blah blah blah. If int v1 is larger than int v2, then we return 1. If int v1 is smaller than int v2, then we return -1. Otherwise, return 0. Okay? All right, let's run the test cases. So first test case, 1.01 and 1.001. That shall give us 0. Second test case, 1.0 and 1.0.0. That shall return 0 as well. Yes. What's the third one? We have 0.1. Okay. 0.1 and 1.1. That shall return -1 because the first one is smaller. All right. We have version 1, version 2. Compare version 1, version 2. Run it. We pass our test cases. Coming here. Run here. And then we're going to submit. Okay. Submit. We pass 602 days. Apparently, it's a slower, but that's fine. This is what 165. Yeah, that's fine. That's like it. Split on dot. Zip longest with 0 as fill, and compare from left to right. That'll be it. That's O or ON, right? Zip. That's ON. Yeah, it's ON. Well, actually, it's O longest of the two, but I just call it ON. 51, 29. All right, let's see what type of method did we use in the past. I believe one of these must be the same. I don't know, it's the other. So this one I int everything and zip longest, so it's exactly the same. How about this one? I don't think this is also split. This is, I don't know, I can do zip longest. Okay, that's fine. All right, so we're done with this. I kind of want to do LRU cache again. For no reason, for no particular reason. I just want to do it again. And I've done it in the past. I just want to do it again. I want to see how this can be implemented. I remember it's a doubly-linked list, and I created a doubly-linked list. But I kind of feel I can use a deck for this, right? So least recently used. So initialize with a capacity, and this is going to be a dictionary, that's for sure. And I'm going to put key and value into it. Update a key if it exists, otherwise add key value. If the number of keys exceeds the capacity from this operation, evict the least recently used key. So the ideal is if we have a linked list, right? If every time a new key is pushing in, I push into the right end, and those are most recently used, and the ones on the left side is the least recently used, right? So I can just pop those. Okay, so which means if I push in a new one, right, and if it's at capacity, we always pop. But is that the least recently used? Hold on. So let's say I just use this one, all right? I just use one, and then I pop it. Hold on. So the current is at capacity, right? The current is at capacity, and then I have this and this. Yeah, let's say I just used A, and A is also at the end because I used A a long time ago. But I do A, right? So now I'm gonna push in a new thing. Then if I pop A, that's not right because A is already used. So I can't just keep popping. The least recently used. I mean, what I can do is hold on. So the deck has a size, right? So I have all the keys in the deck. So the least recently used is the one that's mostly to the left. The mostly to the left, those are the least recently used. Not really. Not really, because every time on the right I add one, right? So I mean I know how to solve this using a priority queue. And that's actually quite trivial to use to do a priority queue. But I kind of want to revisit the doubly-linked list because I remember I think that's a brilliant idea. That's genius. I never really remember how. I mean, if we can, right, I can move the the node from the front to the end. Right? Every time I use it, I just move it. Then whenever we call it on the front, on the left side, will be the least recent used. So how can we do this? How can we do this efficiently? We keep yes, we just the dictionary, right? So the dictionary will store the node, the what should we call it, the address, right? The address of the node. So it's gonna be two values. It's gonna be key value and the node, right? The node. So every time a new the same key gets pushed in, I will look into the dictionary and take the node, and because it's a doubly linked list, I can cut it out from the linked list and push it onto the right side, right? And once I do that, it will be at the end. Okay, so does Python has a doubly linked list? I don't think Deck is a doubly linked list though. Python built in. I know last time I created a doubly linked list myself, but I kind of don't want to do it again. I'm a little bit lazy. I don't think so. It's a deck. Yeah, but I don't think deck can do 01 of cut and paste. Not cut and paste. Oh my god, what am I doing, man? Collections. A list-like container with fast appends and pops on either end, and that's all it does on either end. It doesn't do like if you pop in the middle, it still takes ON. Wait, hold on. What does it say? Yeah, it's a stack and queue, so it doesn't do. It just do 01 on the append, prepend, and append. Well, let's read ourselves. Why? No reason, just for fun. Let's try it right here. So what do we want? So we need a capacity. That's fine. So we say self.cap equals capacity. Oh, we also need a linked list. So we need, let's say, class node, list node. Okay, list node. Initiate self. What do we need? The node. I don't even need a value. Oh, we can put a value. We can put the value in, and then the dictionary will only be storing the index, not index, the address. So okay, let's say value. That should be it. So self.val equals val self dot pre, right? We have a pre, and self dot next. Let's call it prev, right? So that's the node, and then we do the cache, and do we have a dummy node? a dummy node as the start. Okay, so we have to do the dummy node. Let's say self.dummy is equal to a list node. Okay, so dummy will be the starting point. Oh, val equals, let's pick a val that will not be used. Value is 0, so -1. So that's a dummy node, will serve as the root for, we can actually just call it root. Yeah, let's call it root. I'll call it dummy, let's call it root. So we have capacity and we have to use the, we can decrease the capacity, right? So the capacity is 0, so yeah, that's very fine. So we have the root capacity, and then what? And then we need to, that's a list node. Okay, we need to do some functions. We can say add. Add will be added to the, so we add, right? So add self. When we add, we just need a value, right? We need a new value, and don't have to return anything, right? This one don't return anything. So how do we add? We always add to the end, right? How do we add to the end? How do we add to the end? Well. Are you thinking what I'm thinking? So instead of saying root, they shall say end. Right? We always point into the end. We always point to the end. But as we grow, right? As we grow, we move it to the end. As we grow, move it to the end. It doesn't really matter because we can just take away and move to the end. So this is not root. We're gonna call it, this is the end, right? And then, oh, and also the dictionary, self.hashmap equals this. Okay, so add, we just find the current end and just add one more node. So we say self.end.next equals list node, val equals val, right? And then we say self.end.next, right? Because we added previous, actually I had pre is easier. Pre equals self.end, right? Because we need to link them together. So this is now linked. Because this pointing here, then this one will pointing back, and after that, self.end will equals self.end.next. Okay, so that's that. But we have to also update self.hashmap, right? Equals, no, not equals, val key. Oh, I need key value. I need key and value. So the key, right, will equal to what? Equal to self dot end dot next. Right. So this is to get the dictionary. Get the address. Right. So we push it there, and self dot and move in there. That's it. That's add. So def remove. Right. Remove. How do you remove? We need to remove. Actually, I don't like this. I should just add the node. Yeah, I should just add the node. Call it list node. And then I can just say this one equals node and node.pre. Make it easier, right? Node.pre equals this. Hash map equal to node and self.end equals node. Right? So we're passing the node. Okay, that's add a node. So remove shall be remove a node, right? Remove a node, right? We should remove a node also. How do we remove a node? So I already know the node. I know the node from the hash map, right? So what do? Well, what we can do is I know the node, so I know the pre, I know the post, right? So what I do is I say node dot pre dot next equals node dot next, right? Node dot pre dot next equals node dot next, okay? Node dot next dot pre equals node dot pre, right? Node dot next. What if it's the last one? Good point. But node dot pre dot next, that's fine. And then it should be if node dot next, then node dot next dot pre. If it's not, then we don't have to consider the, because this will just point into, yes, it will just point into none. Sorry, so if node dot next, then node dot next dot pre equals node dot pre, right? So by doing this, I have cut out the node, right? So the node doesn't exist anymore. And then all we need to do is to so I'm going to remove it, right? So remove it, and I need to say del self dot hash map key, right? Or remove the key, and that's it. Okay. So now what do? That's remove and then remove the key. So the get, right? When the get, if it exists, then we say if key not in self.hashmap, right? If it's not there, then we'll return -1, right? Easy peasy. Otherwise, we're going to return hashmap, self.hashmap, key. This points to the node and val, right? That's get. Put a key in, right? Put a key in. How do we do this? We say if, right? If self.capacity, if we have capacity, well, if self.capacity is 0, if we don't have capacity, then we need to remove the head. Oh, I only have end. I might need a head as well. Hold on. How do we do this? Yeah, we have to have head. So we have a head. That's also the end. And then as we grow, right, grow, but this head, it doesn't point into anything. Which is fine, Yes, that's fine. So as a head, and self.end will equals to self.head. Okay? So when you add, we're looking at the end, and then we move end down. Head stays put. Head never moves. And when you remove, right, I say I'll grab a node to remove. Okay, so I grab a node to remove, and this is just the remove part. But where is the key? You need a key. Here is the same thing, so I need a key. So each node I have to have the key and a value. Okay, that's fine. Self.key shall equals the key. So we need a key and a value. So key equals -1. Doesn't matter what's the key. Yeah, that's fine. So this is all fine or good. So node, blah blah blah, and this is have to be node.key equals node, right? That's fine. When you remove, it's the same thing, but hash map node.key. right? So I have to remove the key. Now when we get, this is fine, hash map key, this one will look for the node and I return the value. Now this, if the capacity is 0, then we need to remove whom, right? Remove whom. So we say self dot remove. Which node to remove? Self dot head dot next. That is the one to remove, right? So we remove that, which will reduce this, right? And after remove, we can put in a new one. So we call self dot add list node, right? It's basically the new list node. Key equals key and val equals value, and that's put. Okay, so let's try it. Oopsie doozy, is not correct. All right, output. Ooh, what the heck? So what happened? No, one. No. So no. One is good. Putting this is no. And oh, get. My bad. Get is used. I didn't change that. So when you do get, we need to move. Oh, my bad. My bad. If it's not there, that's fine. Otherwise, we need to move. So we're gonna call self dot remove self dot hash map the key. Right? We're gonna remove this node and self dot add self dot. Ooh, wait a second, because I already removed. I point in the node because it's already deleted. All right, so let's say node equals this. Right, node equals this. So I remove this and I put it back in, right? And I return. I already get it, so I can just return node.val. How about that? So this is to update, right? And the capacity is 0, I'll just remove this, right? But I don't add it back, and I add a new one. Doesn't matter. Okay, so I'll try it again. Ew, it's still not right. Hold up. Output 2. Shall we return -1? How? When you get, right? Key. Hold on. So I get 1, right? I get 1. Key is in hash map, and I get the node. I remove the node, right? I remove the node, and I delete it from the hash map, and then I add the node to it, right? I add the node to it. I delete the node. Okay, this one should be fine. No, value turn 1, and 1 should be at the end. 1 should be at the end. And then I put, right? I put 3. So I put 3 and a capacity. Oh, I never decremented capacity. My bad. That's why. So we add it and self.cap minus equal 1. Yeah, I forgot to decrement the capacity. Oh my god, still wrong. So this is good. All right, get 2 not found, and I will put 4. Right, and I put 4, 1 shall get removed. But 1 is not removed. Now let me go through the whole thing. I have 1, I have head, right? And then 1, end is on 1. And then I got 2, right? Then get 1. When I get 1, I remove 1 and put it here. Then I put 3. When I put 3, capacity is full. So I remove head on next. So I remove this, put 3, right? And then I put 4. I shall remove 1, right? I shall remove 1. So 4. And then get 1. Okay, so why is 1 not removed? I don't know. If this is equal to 0, then I remove. Right? If it's not equal to 0, I do this. I think this one is wrong. If capacity is 0, I'll do this, and capacity should be plus equal to 1, right? Yeah. There we go. That I think is right. Oopsie doozy. None has no next. What the heck happened? Node.pre. How? Node.pre.next equals node.next. Get. Capacity is 1. Capacity is 1. Okay, capacity is 1. And I put, because I have a head, right? I have a head. So if capacity is 1, I have a head, and I put 2, 1, and I get 2. So when I get 2, I will remove. So it's head and 2. So I remove 2, right? I will remove 2. So node.pre.next or equals to node.next, which is nothing. And I see the problem. I didn't handle the case of next, not next. Didn't handle the case of and when you remove. When you add, you just end and keep going. When you remove, it depends, right? If it's So node.pre.next equal to node. This is always right. If node.next, then I do this. If it's not, right? If node is the last value, right? We say else if node is the last node, then self.end equal to node.pre. Now let's try this. Both pass. Okay, let's try this. Oopsie doozy. Wrong again. Key error. Huh? How? How do we have key error? When you remove the node is always there, which means it shall be in the hash map. Okay, so we put 2, Oh my god, the key can be this. Wait, that's hold on. I can I forgot. Oh my god, you can update. My bad. You can update. Okay, hold on. So every time you put, right? So when you put, every time you put, I need to get it first, right? Every time you put, because I want to update it. So every time you put, I will get first. If I get is -1, hold on, get will remove it and put it at the end, right? Therefore, if it doesn't exist, so I say if self.get key is smaller than 0, right? If it's smaller than 0, which means it doesn't exist. And then I say if I have capacity, that means we have to add a new one. Otherwise, it's going to be update, right? Else, because I run this and return the value, it's already at the end. Else, we just say self.end.value will equal to the new value. All right, let's try this. Oh, this is not that easy, huh? All these edge cases. Yep. Okay, try it again. Oh my god. I think this data structure is not as good, right? Nah, I think this data structure is not as good. I don't like it. I don't like it at all. It's giving me so much trouble about the update and stuff. How? When you remove, it says the key is not in there. I remove the node. So when you get, I always remove the node first. If it's in there, I will remove the node, which is delete, and then I add the node. But when I add, I'll add it back, right? So I always, so the key is in there, so hash map key is available. And then I remove the node. So remove the node will delete the key from the hash map. And I add the node, I'll add it back into the hash map. But why would this be wrong? This is too much for me to even recognize. Again, get. Right, get is a call. So if key is not in hash map, it's a -1. If the key is in hash map, so the rule is if it's inside the hash map, it must have a node. Right? So I grab the node and I remove this node. Right? Every time I remove this node, I will also, you know what? I think this is causing trouble. So let's handle this. Let's handle this outside. So the add do one thing at a time. So let's not do this here, okay? So let's not do these here. So the add and the remove only handles the doubly linked list, right? So we make sure that the doubly linked list is correct. So they only handle this. And then when you say get, right? When you get, no matter what you do, when you get, we shall not change the hash map. So I grab this, I just remove it and put it at the end. That's it. So the get doesn't change. So what changes is here, right? So you put, and we will try to grab it first, right? Dot key, try to grab it first. If it's smaller than 0, which means it doesn't exist, then I see if the capacity is 0, then I need to remove the head, right? And once I remove the head, remove the head on next. Remove head on next. So the remove shall return to me a key. Okay, so remove shall return to me a key. What if capacity is 0, right? What if capacity, can capacity be 0? Capacity has to be 1. So I add this, and capacity minus 0, 1. Otherwise, because of this, the node will be at the end. Add. I'll remove this head on next, which is fine. So this one I want a key. So I want to remove blah blah blah. So the node is the one to remove. So actually I have the key. So I say key or equal to self.head.next.val.key. So I have the key and I remove it and I delete it. So del self.hashmap. So I delete the key. And then if it's smaller than 0, it doesn't exist, and I add. Right? When I add, I need to create a new node. Let's say new node equals this. Okay. And add node, capacity to this, and self.hashmap key equals to the node. Okay, let's put this one here just to check. So many edge cases. Still problem. So it didn't really solve the issue. How? What is this key? I'd say if key is not in self.hashmap as print key, the key is full. Oh yeah, I know the key is full. Which means full needs to be removed, right? And something happened that it's inside I mean, if it's on this path, it's not. So the key, oh yeah, the key is not in the hash map. The key is not in the hash map, but self.head.next key is in. How is that possible? All right, let's go through again. Add, right? So linked list, I have an end, I have a head, and end keeps moving, right? So when we add something, we always add to the end. So self.next.end.next equals the current node, right? Okay, node.pre would equal to this, and self. This I think is fine. Remove, right? Remove. I will always remove. It could remove any node. So I say node.pre is the previous node.next equals node.next. That's correct. If node.next, which means if it's not the last node, right? If it's not the last node, then node.next.pre equals node.pre, right? Node.next.pre. So this one pointing back. So that's also fine. And because it's not the last one, it doesn't hurt on the end. And if it is the last one, then I say the node is the last one. So node.pre.next equals none, which is the none, right? And self.end equals node.pre. That also makes sense. So I think this is also right. So we get, right? To get something, I need to check. I need to check if the key is not in hash map. So the rule of hash map is if the node is in the linked list, it must be in the hash map. Otherwise, it's not in the hash map. I say if key is in hash map, okay, so the key is not in hash map, then I return -1. No, nothing moves, right? Otherwise, the key is in hash map. I grab the node from the key. I will remove the node wherever it is because I just used it. So I remove the node and I put it back, right? So I can remove it from anywhere in the linked list. And I have to remove it and I add it to the end, which is fine. And every time I add, we always add to the end. And what if I remove the end? So what if the node is already at the end? What if it's already at the end, I remove it, right? And because it's already at the end, after I remove it, self.end will equals node.pre, right? So self.end is here. And then I add it again, which basically do it again. It's all fine. So this get is fine. Now the problem is put. Okay, so to put, I need to first check if the key is in it. If the key is inside, and because I call self.getKey, and if the key is inside, I will already do this movement. Like node will come out because the value, right? The value is 0. So if it's smaller than 0, right? Smaller than 0, that means it doesn't in. So if it's 0, then we go here. Then because of these movements, it's guaranteed because I remove it first and I put it back. The guarantee self.end is pointing to the new node, right? Self.end is pointing to the new node, and because the key is in it, we don't have to change anything. Hold on. I remove it, right? When I got a node, and I remove the node. Okay, so all I do when I remove the node is to make the other links. So the node is still there, right? And I added it, which is self-end equals the current node. and node. Hold on. I think I might find out. So when you add, this node is guaranteed. You know what? I don't know if it's guaranteed, so I need to guarantee it myself. So I say, now this node has to be guaranteed to have nothing and nothing. So it must be a new node. Okay? When I add, it must be a new node. When I remove, right? When I remove, I handle the others, which is fine, and I need to cut the tie. Say node.pre equals node dot next equals none. I cut the tie. Now let's try. And also I don't have to print. Now let's try this. Yes. Okay. Now let's go. Ooh. 3 errors. 3 errors. Come on, man. Let's check the previous solution. Yeah, the problem is this. I didn't clean out. Yeah, you have to clean out the node. I did not clean out the node. That's why it was wrong. Okay, head and tail, cache, capacity, count, remove, add, move to head. Good one. Get. Cache key down value equals value. Move to head. Yeah, I think it's similar, but how do you do the remove? Have a pre, have a post. I didn't really delete this. I think it's the get. I just move, I remove, and I add. The same as what I did. I remove it and I add. Oh, look at this. Ah, that's why. Here, head and tail are static. We just add things. Ah. Yep, this is a better design. This is a better design. Avoid a lot of this. Here, only the head is static. The end is not static. That's why when you remove, it is possible to remove the last one. I go, why you even design it this way? If you don't remove the last one, then everything's fine. I see. Everything else is the same. But why it took so long this time? Yeah, I'm doing this because I want to do this. LFU cache. That was, I'm trying to warm up myself to LFU cache. So yeah, I'll do this some other time. All right, let's see. 22 test cases. This is the same number of test cases. I don't know. Well, man, I do have a couple extra steps, I guess. I have del. I'm not sure. Do I have delete operation here? I do. It's fine. All right, that will be it for right now. I'll see you guys later. Adios.